Hi everyone, this is C3 Local Linear Approximations. You can see the objectives that we're going to use here. We're going to write the equation of a tangent line at a point to a curve. We're going to use that tangent line approximation to estimate the value of the function, and then we're going to use concavity to determine if the approximation is an over or under estimate. So let's begin. So there are two important concepts that are at play in these linear approximations, and one of which is that all functions, if you zoom in on them as close as possible, they all turn into lines. You can kind of see an example of this right here, where it talks about this curved line, right, the square root function, and how this tangent line, if I were to zoom in on this point 93, eventually, it would just look like a line. In fact, it would look like a line with the same slope as the tangent line at that point. And so if I had a point, an x value that was a little bit bigger than 9 or a little bit less than 9, I could actually use this tangent line to approximate the value at that x coordinate. And then I could also take the second derivative of my function and use concavity to decide whether the tangent line was above it or below it. So you have a couple of things going on here. This local linearity, this fact that if you zoom, you end up on a line. And also that if you can find the equation of the tangent point, the tangent line, then you can use that tangent line to approximate. So the method to do this would be pretty simple. So for instance, if you're going to write the equation of a line tangent to a curve, right, then at this point, and the function is the square root of x, then what you would do is take the derivative of the square root of x and then substitute that value in there. All right, so this would still be, this would be x to the 1/2. So then taking the derivative of that, that would be 1/2 x to the negative 1/2, right, or 1 over 2 square root of x. We haven't done this in a little while, but that's exactly how you do it. All right, and so then if you're going to write the equation of the line tangent, you need a point and a slope, and I have a point, so I would do y minus 3 equals, I'm going to wait for my slope, and then I'm going to do x minus 9. And so that's going to be the beginning part of my equation. Then what I want to find is I want to find the derivative at that point. So I'm going to find f prime of, and I'm going to use the 9. So this will be 1 over 2 square root of 9. Square root of 9 is 3 times 2, so this is 1/6. So there is my equation of a tangent line. All right, then what I want to do is in order to use it to approximate another value, I might want to make this into y equals mx plus b. That might make it easier. It doesn't necessarily, but with that fraction there, it might. So another thing that I could do is just put the 9.01 in there and use a calculator. And so that's probably what I'll do here. So I'm going to do it like this, though. I'll say 1/6. X is 9.01 minus 9. And then I'm going to add 3 to the other side. All right, so then when I do that, and I put that in my calculator, I'm going to end up with 3, right, because the square root of 9.01 is going to be a little bit bigger than 3, 3.001666. Okay, and so it's very close, very close to the square root of 9, which is the one at the point. Okay, so later on we'll look at exact ways to find that value, but this helps us approximate it. So I really liked these visuals here because it reminds us then what concave up and down mean, right? So for instance, you see this area, this is all concave down. Then there changes color. So right here at the change of the concavity, that's going to be the inflection point, right? And then change again, and then change again. And so on this, you can actually see concavity. On here, what you can notice then here is that if you drew a line through the inflection point, the tangent line through the inflection point, you would see that when it was concave up, all the tangent lines are below, and then when it's concave down, the tangent lines are above. So if something is below, then that would be an underestimate, and if it's above, then it would be an overestimate. So again, briefly, you can kind of see what's happening here. This is just another way of seeing it's not as pleasing as that other one, but you can see that f is concave up. That'd be the green right here, the green. And then you can see that the second derivative is positive, right? So if the second derivative is positive, then the derivative would be increasing, right? So I've got concave up. The tangent line is below the graph, and the secant lines are above. If the function is decreasing, right, still concave up, both of these are concave up, then the tangent lines are going to be below, and that would be an underestimate. If it's concave down, either way, whether it's increasing or decreasing, the tangent lines are going to be above, and that would be an overestimate. Okay, one final example that we're going to do. We have f of x is equal to 3 over x to the third, and I have it rewritten so I can take the derivative, right? So I would take f prime of x is equal to negative 9 x to the negative 4, which is negative 9 over x to the fourth. Okay, the point I have been given is 1, 3, and then this is where I'm going to find, I want to find what f of 1.1 is, right? So I find the derivative because what I need to find is the derivative at 1, which is going to be negative 9 over 1 to the fourth power, which is negative 9. And so I would write my equation, y equals, y minus 3 equals negative 9 x minus 1. And it probably would be a good idea to go ahead and multiply this out. So that would be y equals negative 9x plus 12. Okay? So I'm to the point where I have now written the equation of a tangent line. That's this right here. That's sufficient for most things. And then here I put it in y equals mx plus b form. And now I would like to know what is f of 1.1, right? So I'm going to put in 1.1 for x. Probably have to use a calculator, and that's going to get me 2.1. 2.1. All right? And so I know that if x is 1, y is 3. And if x is 1.1, it's 2.1. So, okay, fine. Is that going to be an over or an underestimate? So one way to do this is to take the second derivative. I'm going to take the second derivative of x, right? So I'm going to go, I'm going to change this to blue, but I'm going to go back to this one, right? So that's going to be 36 x to the negative 5. So that means that we want to pick a point, a test point on our, because it's going to be at 0 because you cannot divide by 0. And then if we picked a negative number on one side of 0 and a positive on the other, if I put a negative in here, this value is going to be negative, and that would be concave down. And then on the right side, if it's positive, that will be positive, that will be concave up. And we know that on concave up, since my x value is on this side in this interval, concave up would mean that tangent lines are along the bottom, and this would be an underestimate. So in class, I gave you 4 problems, and they all have all of these steps. So this is just exactly like one of the problems that you will encounter for this concept. So use this example, work those problems in class, and I will see you there.